Hello everyone, am I audible? Can you hear me?
Namaste, sir.
Yeah. Give me some time, I'm just getting the host access.
Sir, namaste, sir.
Namaste. Just give me
Sir,
2 minutes, getting the host access. After that we can
sir, your
start.
voice is low, sir.
Hello, is it fine now?
Now fine, sir.
Just give me 2 minutes, I'm getting the host access and then we can start.
Yes, sir.
Yeah. Am I audible?
Yes, sir.
Yeah, can you see the screen?
Yes, sir.
So now we'll be dealing with the questions of Newton's law of cooling, right? So Newton's gave a theory for the law of cooling where he gave that mc T1 minus T2, and T2 is the final temperature after time T, is equals to K T minus T naught. Okay, that is equals to K times T1 plus T2 by 2 minus T naught. This T is average of the initial and final temperature. So T1 and T2 are initial and final temperature, and T naught is the surrounding temperature. Okay, so this was the formula given by Newton's laws of cooling. Understood? Now, so we have a question here for this. A body cools down, body cools down in 7 minutes in 7 minutes from 60 degrees Celsius to 40 degrees Celsius. From 60 degrees Celsius to 40 degrees Celsius. All right. What will be its temperature? What will be its temperature after next 7 minutes? After next 7 minutes. Temperature of surroundings. Temperature of surroundings is 10 degrees Celsius. Assume Newton's laws of cooling hold good. Try to solve this. Solve this quickly. Any answers?
Sir,
Yeah.
can you tell the formula, sir?
Formula is here written. See at the
Sir,
top.
it's a bit confused, sir.
What is the confusion there?
Sir, in our school, it's deleted questions, sir. So can you teach it a bit elaborately, sir?
Okay, about the Newton's laws of cooling.
Yes, sir.
Okay, now see. Sorry, what did you say before that? The school is?
In CBSE, it's deleted, sir.
All right. See there. Write it down. Basically, Newton's laws of cooling states that, write it down there. The Newton's laws of cooling states that rate of cooling of a body, rate of cooling of a body, rate of cooling of a body is directly proportional to the temperature difference. Rate of cooling of a body is directly proportional to the temperature difference. Is directly proportional to the temperature difference. Temperature difference between the body and its surroundings.
Yes, sir.
Between the body and its surroundings.
Between the body and surroundings, sir.
Yeah. So what happens there? For example, if you have taken a body, temperature T1, surrounding temperature is T2. Okay. So heating, how much heat will transfer from this body? Let us say that T1 is greater than T2. So how much heat will transfer from the hotter body to the colder body depends on the what is the temperature difference. If the temperature difference is greater, for example, let us this is 100 degrees Celsius and this is 10 degrees Celsius, and in another case this is 100 degrees Celsius and this is 90 degrees Celsius. So here more amount of heat will flow and here less amount of heat will flow. Okay, this is what it says. Q1 is greater
Yes,
than
sir.
Q2. Okay, this is Newton's laws of cooling. And based on some integration, derivation is there. He proposed some formulas related to that. So what was his formulas actually? His formula was, if you just talk about the formula, his formula was mc, mass into specific heat capacity, into T1 is the initial temperature minus T2 the final temperature, and time required to change in the temperature is equals to K times average of the initial and final temperature minus the atmospheric temperature, surrounding temperature. Okay. So what you have to do in this question, is first I have to write the first equation mc. So in 7 minutes it decreased from 60 to 40, right? So it will be 60 minus 40, and let us keep it in minutes only, by 7 is equals to K times 60 plus 40 by 2 minus of surrounding is 10, right? So it will be mc into 20 by 7 is equals to K into 60 plus 40 is 100, 100 by 2 is 50, 50 minus 10 is 40, 40. So that means, can I conclude that mc is equals to 140 K, right?
Sir,
Agree?
sir,
Yeah.
can you give me that in another slide, sir? It's too small to see, sir.
Okay, see. So formula was mc T2 minus T1 minus T2, initial minus final temperature, and it took 7 minutes. So 7 is equals to K times average temperature, 60 plus 40 divided by 2 minus of 10.
Yes,
Understood
sir.
till here?
Yes, sir.
So if you solve this, what you will be getting? 20 by 7 here is equals to K times 60 plus 40, 100 by 20, 50 minus 10, 40, 40.
40.
So 20 and 40 gets cancelled 2. So MC is equals to 14K. Can I write like this?
Yes, sir.
Okay, this is my equation 1. Now I have to find the time for which, sorry, the final temperature in the next 7 minutes. So again, I'll be writing the same equation. MC 60 minus 40, sorry, next, let us say that it is now at 40 degrees Celsius, and let us say that it is at T2 degrees Celsius after 7 minutes. So 7 here, right?
Yes,
Now,
sir.
what is again, K will be same because same body we are talking about. Average temperature 40 plus T2 by 2 and minus of 10, right?
Yes, sir.
Surrounding will be same.
Yes, sir.
Instead of MC, can I write 14K? 40 minus T2 upon 7 is equals to K 40 plus T2 minus 20 upon 2. I took the LCM. K cancel, right?
Yes,
7
sir.
times 2, and this 2 goes up. So 4 into 40 minus 4 into T2 is equals to 40 plus T2 minus 20, right? You have to find T2. So it will be 4 into 40 and here will be 20. So 4 into 40, 160. Here from here minus, sorry, minus 20, yeah. And this minus 4 T2 and T2. It goes this side, 5 T2, na? So 5 T2 is 140. T2 will be what? 28 degrees Celsius. Understood? So after next 7
Sir,
minutes, hmm,
can I explain it from where you cancel the key, sir?
you cancel the key. You just have to find T2. You can solve the equation now. You solve it by your way. You just have to find T2.
Yes,
Cancel the
sir.
key. I took this to the other side. It will become 4. I opened the bracket 4 into 40 minus 4 into T2, right? And this side it is 40 plus T2 minus 20. Solve for T2. That's it. Understood?
Yes, sir.
Good. Write it down fast. Have to move on. Today we'll be completing this chapter and moving on to the thermodynamics. Shall I change the slide?
No, sir.
Is it done?
Sir, done, sir.
Okay. So last few questions.
Yes, sir.
See, one is Stephen's law. Stephen's law. You know what is black body? Black body is a body that can accept and emit all type of radiations. All right. So energy emitted per unit area of a black body is nothing but E is equals to sigma T to the power 4. You must have studied this formula. Next is Stephen's Boltzmann law. If you don't know, tell me, I'll explain it. So if a black body is there at a temperature T, yeah,
Explain, sir.
you have not studied it. Okay. See, there's a black body. And if a black body is something like that can accept and emit all kinds of radiations. Okay. All kinds, all different types of radiations it can accept and emit. Different frequencies, different wavelength. So if it is at a temperature T, so the radiating power, radiating energy of this black body will be sigma, that will be specific to a particular black body, what material it is of that, into T to the power 4, the temperature to the power 4. So energy is directly proportional to temperature to the power 4. Now, if the surrounding temperature is T naught and that body temperature is T, then it will be T to the power 4 minus T naught to the power 4. Till here you understood?
Sir, can you repeat it again, sir?
Black body is there. Black body is at a temperature T. So it's
Yes,
radiating
sir.
energy. Yeah. Go on.
Very, sir. I said yes.
Huh. So black body is there. Black body is radiating energies. Energy is what? Energy is form of radiations. All sort of frequencies. That is also kind of radiations, and that contains energy. So black
Yes.
body is at temperature T. So its radiations will be, the energy will be sigma into T to the power 4. That is a formula. Okay. That
Yes,
is
sir.
Stephen's law. So what is Stephen's law? Stephen says that energy emitted per unit area of that black body, if it is at a temperature T, will be E is equals to sigma T square T to the power 4, where sigma is Stephen's constant. Okay, that has a
Yes, sir.
particular value. All right, and that value I'll tell you later after this. Then Stephens Boltzmann, what Boltzmann did, he like modified this law, Stephens law, and he said that if the external temperature is T naught, so that energy radiations will be sigma into T4 minus T naught to the power 4. That that change he created. Okay,
Yes,
and
sir.
at the end, so this was energy per unit area. It is not only energy; its dimension will be energy by area, energy per unit area. Okay.
That means
Now,
we
if
can.
you want to, yeah, if we have the total area, then what will the total energy? So energy will be sigma. Then yeah, one more thing was there. Epsilon. Epsilon is the emissivity, that how much percentage of it can be emitted. Okay, that
Yes, sir.
efficiency basically into t to the power 4 into area into time. Okay, and this is, yeah, per second also. Per unit time, per unit area, how much energy is radiated, this is the E. Same here. So if you want to know the exact energy, we have to multiply with that area and that time interval during which we need to calculate. Understood?
Yes, sir.
So sigma has got different values: 5.67 into 10 raised to the power minus 8 joule second inverse per meter square per Kelvin to the power 4. Okay. Same thing, 5.67 into 10 raised to the power minus 8 joule second inverse is nothing but watt. Watt per meter square per Kelvin to the power 4. And same thing in CGS unit can be written as 5.67 into 10 raised to the power minus 5 erg second inverse per centimeter square per Kelvin to the power 4. Understood? These are three different formulas that you need to remember. Acha, one more thing. Fourth, Wien's displacement law. Wien's displacement law. What he said, that the wavelength corresponding to the maximum energy, the wavelength corresponding to the maximum radiation of energy exerted by a black body is inversely proportional to temperature, where B is Wien's displacement constant, that is 0.0028898 millikelvin. So what Wien displacement law says, that the wavelength corresponding to the maximum energy emitted by a black body is inversely proportional to the temperature. Understood or not? These four important laws, basically three. Hmm?
Understood, sir.
These are easy. You just have to directly use it. They'll be asking you, if at 20 degrees Celsius the energy is E, then what will the energy at 40 degrees Celsius? So questions will be like this. Okay, if total area is A, temperature is this, calculate the energy like this. The all data will be given to you. Got it?
Yes, sir.
Write a question. If after writing this, write it fast.
Yes, sir.
Tell me when it is done.
Okay, sir.
And this is all about this chapter. See, still there are more questions that you need to solve by yourself. We have very restricted time, so I can just help you out with the different types of questions. But in that, to gain confidence, you have to solve more of them.
Sir.
Yeah.
Sir. What is B called, sir?
B is Wien's displacement constant. Wien's constant.
Yes, sir.
Wien's constant. Sigma is Stefan's constant. If you will develop something, you will name it Yashwant's constant, na?
Yes, sir.
So that everybody knows it. That's
Okay, sir.
it. Write it fast. In this restricted time, I can only help you with different types of questions and your doubts. So be prepared for this class. Always be prepared.
Yes,
solve
sir.
more questions. You already know that what we are going to do in the next class. So be prepared for those doubts that you can ask from me.
Yes, sir.
Hmm. Is it written? Tell me if it is done.
Sir, completed, sir.
Completed. Good. Right. Now write a question. A spherical body.
Yes.
Just a minute.
Sir,
Yeah. A
if the
spherical
radius
body
after
with
what, sir?
radius. Sorry.
Radius after what you have wrote, sir?
If the radius were halved and the temperature is doubled, what would be the power radiated?
Okay, sir.
What would be the power radiated? Spherical body with radius 12 centimeter radiates 40-watt power initially at 500 Kelvin. Now what I am doing, I am reducing the radius to half and temperature is being doubled. So what will be the new power radiated? You have to use one of those four formulas that we discussed in the last page. Try to do it by yourself.
Yes, sir.
Any answers? Any answers? Tell me.
Finding, sir.
Do it fast.
Sir,
Yeah, tell me. Tell me the answer. E is equals to sigma A t to the power 4, right? So E is directly proportional to area into t to the power 4. Now this is a spherical body. So what is area? 4 by 3, sorry, 4 pi r square t to the power 4. So can I say that E is directly proportional to the r square and t to the power 4? So E1 by E2 is what? R1 by R2 whole square, T1 by T2 to the power 4. That's it. So E1 was 450 watts, E2 we want to calculate. R1 is R1, R2 is half. So R1 by 2 squared, and temperature is double, T1 and 2 T1 to the power 4. So 450 by E2 is what? 4, and it will be 1 by 2 to the power 4. 2 to the power 4 is what? I guess 16. 1 by 16. So E2 is nothing but 450 into 4. This here 4 and 4 goes there. 1800. Understood? Everybody? Did you understand this?
Sir,
Yeah. Any doubt?
can you explain it again, sir?
So we use this formula E is equals to sigma A t to the power 4.
Yes,
So
sir.
E was sigma was constant for all the cases. So we just took the proportionality, area, and temperature. That was what changing there in this question. In even in
Okay,
area,
sir.
only the radius was changing and T temperature was changing. So we took E is directly proportional to R square and T to the power 4, right?
Yes, sir.
Hmm? So E1 by E2, I took the proportionality. R1 by R2 whole square, T1 by T2 whole square. And the R2 was in the as given in the question, the radius was halved. So R1 by 2. You put that, and T2 is doubled, T2 T1. So we got that 4 here and 1 by 16 here.
Sir,
Then you count for
sir,
E2.
sir.
Yeah.
Calculation part only you tell again, sir. You're going very fast.
Which one? Which one? Calculation.
Calculation
Calculation
part
you can do
after
it
finding the
yourself.
formula.
Calculation you can do it by yourself. It is so easy.
Okay, sir.
See, I'm doing it again. 450 by E2 is R1 divided by R1 by 2, isn't it?
Yes, sir.
That is to be squared. So this 2 will go up and this R1 cancelled.
Yes, sir.
So this will be 4. This 2 go up and that is to be squared. So 4, and that is to be multiplied by T1, and the T2 is 2 times T1.
Two
That is
times
to the
C2.
power 4. So
Yes, sir.
T1 cancel. 1 by 2 to the power 4 is what? 1 by 16.
Yes, sir.
Okay. So this 4 cancels 16 by 4. This is 450 upon E2. So E2 will be what? This 4 goes there. 450 into 4. That's it.
Okay,
That
sir.
is 1800. Now understood? Did you get it? Understood or not?
Sir,
Yeah.
we are removing the proportionality constant.
That sigma we are removing. That was of no use. Even if you apply sigma here, by sigma it will get cancelled.
So, okay, sir. Whichever gets cancelled, you remove it from the formula.
I just took that changing part which was changing. Okay.
Okay, sir.
I just took the changing part. Only radius and temperature were changing. That's why I just found that to which power of radius and temperature this E is related with.
Okay, sir.
At it fast, we'll be moving on to the next chapter, thermodynamics. Tell me when it is done. Done?
Yes, sir.
All right. So next chapter, thermodynamics. Thermodynamics. Okay, we'll be dealing with this chapter now. So basically, for the first thing that we have to do here is see, there are what is the system? First of all, system, the conditions, the considerations. For
Sir,
example, these two bodies. Yeah,
your voice is low, sir.
sorry. So if we have two bodies and we are studying about them, so that constitutes the system which we
Sir,
are studying. Yeah.
your voice is low, sir.
Again, hello. Is it
Yes,
fine
sir.
now?
No, sir, not improved.
Yeah. Is it fine now? Hello. Hello. Can you hear
Sir,
me now? Yeah.
yes, sir.
Okay.
They are increased.
So,
They are increasing the volume here, sir.
oh, so see here. Basically, whatever object we study, that constitutes the system. Okay. And apart from that, everything is surrounding. All right. Everything is surrounding. So there are thermodynamic variables. What is thermodynamics? So basically, thermodynamics is the science that deals with the concept of heat and temperature and how the flow of heat is going on. Okay. What is thermodynamic equilibrium? Equilibrium is there is no like exchange of heat and gases. Understood?
Yes,
So
sir.
there are three thermodynamic laws. Okay. So first one is said to be zeroth law. First one is said to be zeroth law. What is zeroth law? You know why this is called zeroth law and not the first law?
I don't know, sir.
Because it was formed after that. First we found first law and second law. And after that this law was formed. So in order not to change that particular consistency, because it was already named as to be the first law, and this
Yeah.
law was the basic of all the laws. So this was to be named earlier, and we found it later. That's why it is named as zeroth law.
Okay,
So
sir.
zeroth law says that if two bodies are in thermal equilibrium to each other, for example, if A is in thermal equilibrium with C, and simultaneously B is also in thermal equilibrium with C, okay, so in that case both have the same conditions, so A and B will also be in thermal equilibrium. Understood?
Yes, sir.
This is zeroth law. Okay. Then heat and energy. So heat, work and energy are three basically related things, and heat and work are directly related things. How? So for
Okay,
example,
sir.
whenever we heat any object, work is done on the system. Okay. So if we heat it, what will happen? Let us say this is gas. So this will try to expand and it will move the things. This piston will go up and this pulley will roll and this body will come down, right? So you can do work by providing heat, isn't it? Understood or not?
Sir, no, sir. Can you repeat it again, sir?
What
We
am
were
I
just
saying here? That heat and work are two distinct mode of energy transfer. By doing work also you can transfer the energy, or by doing heat also, by providing heat also you can transfer the energy. For example, if you transfer the heat to this gas, it will move this piston up because gas will now vibrate and will try to expand. So it will move this piston up and potential energy of this body will be lowered now then.
Yes, sir.
So we can like change the energy. We can transfer the energy from one body to another body by doing work also and by heating that body also.
Providing heat also.
Got it? Now sign conventions. So if heat is absorbed by a system is positive, one thing. Heat absorbed is positive. Heat released is
Negative.
negative. Secondly, physics and chemistry differs here. Work done by a system. Work done by a system is what? Positive. And chemistry says is negative.
Negative.
And work done on a
On
system
term is negative.
is negative. Okay. This decreases the internal energy. Internal energy. And this increases the internal energy. Understood? Got it or not?
Yes, sir. Got it, sir.
Hmm. So basically, physics is something that believes in working by himself.
Yes, sir.
Chemistry is lazy, right?
Yes, sir.
Okay. So write it down. Written. Shall I change the page?
No, sir. Some are writing, sir.
Yeah, write it fast. Is it written?
Yes, sir. Completed, sir.
All right. Now see, so work done is basically related to work done is nothing but integral of P delta V. There is a derivation there, short derivation. So for let us say that by heating, we like changed the piston's position from here to here, delta X length, okay? And the area of the piston is A by providing P force, P pressure, okay? So what will the work done be? So force is what? Pressure into area, right?
Yes.
And work done is what? Force into displacement, that is X,
Yes, sir.
okay? So can I write P into A into X? And what is A into X? Isn't it volume?
P. Yes, sir.
Change in volume.
Yes, sir.
Okay, this is this change in volume. So work done is integral of P dV from V1 to V2, change in volume. Okay,
Yes.
same thing we can show in the graph also. If you draw a graph, this relation you all know PV is equals to nRT. You have studied in gaseous state physics, chemistry.
Yes, sir.
So P should be nRT by V, Okay, so in case of isothermal process, what is isothermal process? T constant.
Remains constant.
If T remains constant, R is gaseous constant, it's constant. If n number of moles I'm taking, that is to be constant. So P will be inversely proportional to volume. So if you draw a
Volume.
PV graph, this is what it looks like in case of isothermal process only. Okay. So this is expansion. Why? Because you're going from initial smaller volume to final bigger volume. And if I just draw it like this, reverse of it, this will be contraction or compression. Understood?
Expansion compression. Yes, sir.
Got it?
Yes, sir.
But in a cyclic process, see, yeah, one more thing. This is negative work done. Compression is negative work done. All right. Compression is what? Negative work done. And expansion is positive work done. So in a cyclic process, this is a cyclic process which starts and ends at the same place. Okay, D, E, and let us say this to be X. So this is a cyclic process. So what will the work done in a cyclic process? So in a cyclic process, first we have two works. This is the first part, the positive work done. So work one will be area of A, B, C, D, E, A plus, because that is expansion, initial lower volume to final bigger volume. Then what you have to do, then you are at C. Now you are going back. So this is the negative work done. W2, area of, negative of area of A, E, D, C, X, A. And what is net work done? Net work done will be W1 plus W2. And W2 is already negative. So you can do it that W1 minus W2. So what is this? Ultimately, work done, net work done is area under cycle. So area under cycle, this will be the area under cycle. That will be your net work done. Understood? Yeah.
W1, W2 itself, I can't understand, sir.
Okay. I'm explaining it again. See here. We have a cycle, cyclic work done. So you start from A, you expand na. If you're going like this, you expand na. V1 to V2. So A, B, C, you go under expansion, right? So what will the work done? Work done of A, B, C. So that will be area under the curve and the V axis. This is the area. So it will be area plus of area A, B, C, V2, V1, A. Like this. Understood? Now, after reaching C, what you did, you went back to A like this. So this is called a cyclic process where you reach the initial position. Okay. Now this area, this work done, this the compression work done, it is negative. Let us mark it as D. So C, D, A will, yeah.
Work done ABC, how we are deriving, sir?
See, work done is area under the graph, area under the curve and the x-axis. If we have like to calculate the work done in this curve now, what you will do, you will like copy this path and you will find this area.
Yes, sir.
And this area will give you the work done.
Yes, sir.
Okay. So for ABC, this A, B, C, V2, V1, A, this whole length is the area.
Yes, sir.
Marking this whole length.
Yes, sir.
Right? And that is positive because it is expansion. Because if you do pressure into final volume minus initial volume, this will be positive, right?
Yes, sir.
But in going back in compression, the final volume is lesser than the initial volume. So that will be negative work done.
Yes, sir.
So in second case, we have to find this area to calculate the compression work done. This is the expansion work done. Now we are calculating the compression work done. Compression work done will be negative. So that will be negative of area of C, V2, V1, A, D, C, like that. Understood?
Okay. Oh, yes, sir.
Now, what is the total work done? Total work done is work done under expansion plus work done under compression.
Yes,
Work
sir.
done under expansion will be positive and work done under compression will be negative. That's it.
Negative. Yes,
So
sir.
ultimately, you are subtracting this minus this. You are subtracting total area minus this area. What you are remaining with? Aren't you remaining with this area?
Yes, sir. A,
So
B,
that is what
C.
it said. So work done total is area under cycle. That's it. Now
Okay, sir.
understood?
Yes, sir.
Can you calculate work done under this area? So we started with point A, coordinates 4, 1. We ended at point B, 2, 4. Went like this. This is PV diagram. Now after B, we reversed and we went to point C, that is 2, 1, and went back to A. So AB it is expansion, BC it is compression, and CA. So basically there are not two types of process here. In going from B to C, can you see that pressure was constant?
Yes, sir.
So this is called isobaric process. BC is isobaric, pressure constant. Isothermal temperature constant. Understood?
Yes, sir.
And can you see in AC, CA, from C to A, the volume was constant?
Yes, sir.
So this is called isochoric process.
Isoporic process.
You know this?
We know, but not in this graph, sir.
All right. So try to calculate this work done under this whole process.
Yes, sir. Sir, sir,
Yeah. Yeah.
can
Answers?
you zoom in, sir? We can't see the
Zoom in.
values.
1 minute. Is it fine?
Sir. No, fine, sir. Perfect, sir.
Well, did you get the answer?
Sir, sir,
Tell me the answer.
3 joules, sir.
3 joules.
Uh,
Yeah, that's correct.
yes, sir. Thank you, sir.
But there is little difference here. See, if I write this in meter cube, then you're correct. But if I write this in liters, then you have to convert this in meter cube, and that will be 1,000 liters is 1 meter cube. So you remember this conversion, right? Got it?
Yes, sir.
That's it. So if this option is in liters, then you have to convert it into meter cube, then you have to find the area. Always check the unit there.
Sir, I can't understand what you're saying, sir.
Okay. So if it is liters, okay, then it is 3, if this pressure is in pascals, so it is 3 pascals into liters, and that is not equals to joules.
That is 3000 pascals, sir.
No, it will be 3 into 10 to the power minus 3 joules. Okay.
Sir, no, sir, I can't get what you're saying, sir.
What am I saying? For example, it was centimeter cube. So you would have converted into meter cube now.
Yes, sir.
Similarly, if it is in liters, sometimes the volume is given in liters. So liters also
Yes,
you
sir.
have to convert it into meter cube. And that's what I'm
Yes, sir.
saying, that if this is meter cube, 3 joules is correct. And if this is in liters, so you have to multiply it with 10 to the power minus 3. That's it.
Okay, sir. Understood,
Understood?
sir. Yes,
Good.
sir.
Okay, then. Thank you, everybody.
Thank you,
And
sir.
please be prepared for the next class. We'll have more questions.
Okay, sir.